When you see an astronaut floating in space, it's easy to assume they've lost their body weight. Do they actually weigh zero? Here on Earth, we mix up our terms. When someone steps on a bathroom scale and says they weigh 60 kilograms, they are describing mass, but using the word for weight. To get the science right, we separate these ideas. Mass is the physical matter inside an object, measured in kilograms. Weight is gravity's pulling force on that matter, measured in newtons. We connect them. Weight equals mass times gravity, or W equals mg. Your mass, the physical stuff making up your cells and bones, is a constant. That means the weight you feel pushing down on your feet depends entirely on the gravitational pull of where you're standing. Let's test that formula. If you have a mass of 60 kilograms on Earth, we find your weight by taking that 60 and multiplying it by Earth's gravitational pull, which is 9.8 newtons per kilogram. You get a weight of 588 newtons. Now, move that exact same person to the moon. The moon is much smaller than Earth, so it has a weaker gravitational field. The 60-kilogram mass hasn't changed, but the moon's gravity is only 1.6 newtons per kilogram. Multiply those together, and your weight on the moon is just 96 newtons. We see this change on Mars. Question 2 describes a 90-kilogram astronaut. Question 1 gives Mars a gravitational field of 3.6 newtons per kilogram. Pause the video here and use the W equals m times g formula to find the astronaut's weight. By multiplying the mass of 90 kilograms by the Mars gravity of 3.6, we get a final weight of 324 newtons. These calculations show that weight isn't a fixed property of your body, it's a force that fluctuates whenever the gravitational field strength changes. Your mass stays put, but that downward pull depends entirely on the planet beneath your feet. Sometimes we have to work this equation backward to find a missing mass. Look at question 3. We have an empty bag with a mass of 0.5 kilograms. When we fill it with 30 identical pucks, the total weight on Earth is 17.64 newtons. To find the total mass, we rearrange our formula to m equals W divided by g. We divide that weight of 17.64 newtons by Earth's gravity of 9.8, which gives us a total combined mass of 1.8 kilograms. From there, we subtract the mass of the empty bag, 0.5 kilograms, from the total. That leaves us with 1.3 kilograms for the 30 pucks. Dividing that 1.3 kilograms by the 30 pucks gives us the mass of a single puck, 0.043 kilograms, or about 43 grams. By isolating mass this way, you can calculate the physical makeup of an object, even when you can only measure the force it is exerting. It's the same logic engineers use to verify the mass of equipment based on how much it weighs before a launch. Mass is the amount of matter in an object, measured in kilograms. Weight is the gravitational force acting on it, measured in newtons. Mass is a scalar quantity, staying constant everywhere. Weight is a vector quantity, changing across different gravitational fields. This explains exactly what is happening to our floating astronaut. Because they are in an environment where gravity isn't pulling them toward a planet's surface, their weight is 0 newtons. They are weightless, but their physical mass hasn't decreased by a single gram. Understanding the difference between mass and weight is the first step to understanding how objects behave across the solar system. If this breakdown helped you, please subscribe and share the video.